Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
It's probably the biggest question we humans ask ourselves, isn't it, when we look up at the stars? Are we actually alone?
Absolutely. It's fundamental. And for, well, most of history, it was pure speculation, maybe philosophy.
Right, just wondering. But lately, things have changed. We've actually started getting tools, ways to approach this mathematically.
Exactly, which is kind of mind-blowing. We've moved from just asking the question to trying to calculate probabilities. What's the actual chance we are the only technologically advanced life out there, at least at our level?
And we've had some classic tools for this, things like the Drake equation, the Fermi paradox concepts many of you listening will know.
Yeah, the cornerstones of the whole SETI field, really.
But today, we're diving into something newer. A statistical framework that builds on those classics tries to refine the question. It's called the Solitude Zone.
This idea comes from Dr. Antal Veres, published in Acta Astronomica. And it's important to get this right away. The Solitude Zone isn't, some empty patch of space.
No, it's not a location.
It's a statistical concept. It's about defining the specific conditions, the mathematical window, where the probability of finding exactly one civilization like ours is, well, higher than finding none or finding many.
Kind of a statistical Goldilocks zone for cosmic loneliness?
That's a good way to put it, actually, a sweet spot.
So our mission today is to unpack this new model. We'll walk you through the ideas behind it, the math, don't worry, we'll keep it clear, and then look at what it might tell us about where we stand. Are we in that solitude zone right now?
And to do that, yeah, we definitely need to lay some groundwork first. Dr. Veres' model doesn't exist in a vacuum. It builds directly on some really key concepts.
Okay, let's start there. Before we get to the solitude zone itself, let's quickly refresh those classic ideas. They're essential because they really set the stage for the problem Veres is tackling.
Couldn't agree more. Foundational stuff.
So first up, the big one, the Fermi paradox, named after Enrico Fermi, the physicist.
Ah, yes, Fermi's famous lunch question.
Exactly. It's deceptively simple, isn't it? The universe is incredibly vast, incredibly old. There are billions, maybe trillions of places where life could potentially arise.
Statistically, you'd expect it to have happened many times over. And given the age of the universe, some civilizations should be vastly older, vastly more advanced than us.
So Fermi's question was just, well, where is everybody? If they should exist, why haven't we seen any evidence? No signals, no probes, no giant space structures, just silence.
And that silence is the paradox. The math suggests a crowded universe, but observation suggests an empty one. And there's still no single universally accepted answer.
But the attempts to answer it are crucial for Veres' model, particularly the idea of great filters.
Right. Great filters. These are proposed as extremely difficult steps or hurdles in the evolution of life or even civilization that are statistically very, very improbable to overcome.
Like bottlenecks, choke points.
Exactly. If a step is incredibly hard, it acts as a filter, drastically reducing the number of civilizations that manage to get past it.
And looking back at Earth's history, we can point to potential candidates for filters we might have already passed. The source material mentions abiogenesis, the actual origin of life from non-living matter.
That's a big one. If that chemical jump is exceptionally rare, maybe a 1 in a trillion kind of event across the cosmos, that's a massive filter right at the beginning.
Another example often cited is the jump from simple single-celled life, like bacteria, to complex multicellular life.
Yeah, that took billions of years on Earth. It wasn't a quick or easy transition, suggesting it might be another major hurdle.
Okay, but here's the unsettling part of the great filter idea, and something Veres definitely uses. Maybe the filter isn't behind us.
Maybe the hardest step is still to come.
Could it be something like, developing technology that inevitably leads to self-destruction, nuclear war, climate change, runaway AI?
Or maybe it's an environmental collapse or some technological barrier we haven't even conceived of yet that prevents civilizations from becoming truly interstellar.
And figuring out where that filter might lie behind us, making us incredibly lucky survivors, or ahead of us, posing a future threat that's a key variable Veres manipulates in his model later on.
It really is. The placement of the great filter fundamentally changes the probabilities. But okay, if we're talking about filters and advancing past them, We need a way to measure that advancement.
Which brings us to the second classic concept, the Kardashev Scale.
Developed by the Soviet physicist Nikolai Kardashev back in the 60s. It's a really clever way to categorize civilizations.
And it cleverly sidesteps all the messy questions about what aliens might look like or think like. It focuses purely on something measurable. Energy consumption.
Exactly. It ranks civilizations based on the amount of power they can harness and utilize.
So there are three main types, right? Type 1.
A Type I civilization has mastered the energy resources of its home planet. It can capture and use essentially all the solar energy hitting the planet, plus geothermal, wind, tidal, the whole planetary energy budget.
Total planetary mastery. Okay. Then Type 2.
Type 2 is a huge leap. This civilization controls the energy output of its entire home star. We're talking about maybe building megastructures like a Dyson swarm or a Dyson sphere to capture that immense power.
Mind-boggling scale.
And Type 3. Type 3 is the peak, really. A civilization that can harness the energy output of an entire galaxy. Billions of stars worth of power. Almost unimaginable.
Okay, so we have the scale from planetary to stellar to galactic power usage. Where do we, humanity, fit on the scale right now?
Well, the estimates Veres uses, and they're pretty standard, place us at about 0.7. K0.7.
0.7. So not even a full Type I civilization yet.
Not yet. We use a significant amount of planetary energy, obviously, but we're far from harnessing the total available energy of Earth. We can't control our climate reliably. We don't capture all incoming solar radiation.
We're still largely dependent on finite resources, subject to planetary whims like weather.
Precisely. We're maybe aspiring Type I,
Yep.
but we have a way to go.
And this K0.7 rating is absolutely crucial for the Solitude Zone discussion, because that's the specific level Veres is testing.
Right. The question isn't, are we the only life? It's, are we the only civilization at this particular K0.7 level of technological development in the entire observable universe?
That specificity makes it a much sharper question, which leads us to the third classic tool Veres adapts, the Drake equation.
Ah, Francis Drake's famous equation. The first real attempt to put numbers, however speculative, on the likelihood of communicative alien civilizations.
It's essentially a chain of probabilities multiplied together, right? Starting with things we know reasonably well, like the rate of star formation in our galaxy.
And moving into factors that are much less certain, like the fraction of stars that have planets, the fraction of those planets that could support life, the fraction where life actually evolves.
The fraction that develops intelligence, then technology, and finally the fraction that's currently broadcasting signals and for how long they do it.
It's a great framework for thinking about the problem, but many of those later terms are essentially educated guesses at best.
Now, Veres uses the structure of the Drake equation, that idea of multiplying probabilities, but he makes a critical change to its scope.
Yes, this is important. The original Drake equation was focused on calculating the number of civilizations in our galaxy, the Milky Way.
But Veres is asking about singularity, being the only one. And if you're asking that, you can't limit your search to just our galactic neighborhood.
Exactly. To test for uniqueness, you have to consider the entire stage. So Veres expands the search area to the entire observable universe. Dramatically bigger playground.
Okay, so let's recap the building blocks. We have the Fermi paradox asking, where is everyone? The Great Filter concept offering potential explanations for the silence, the Kardashev Scale giving us a specific measure of our current level, K0.7, and a modified, universe-wide scope inspired by the Drake equation.
That's the foundation. Now we can really dig into the Solitude Zone itself.
Right. Section 2. What is the Solitude Zone, mechanically speaking? Because this is where the new statistical thinking comes in.
Okay, so Dr. Veres defines it formally as the region within the possible parameter space, all the potential values for things like how often life arises, where the probability of exactly one instance of life at a certain complexity level, let's call it px1, is maximized.
Maximized compared to what?
Compared to the probability of 0 instances, px0, and the probability of more than one instance,
Okay, and you mentioned this forces the math into a different shape than, say, optimistic takes on the Drake equation.
Yes. If you plug optimistic numbers into Drake, you often get this sort of exponential curve. If conditions are good, the number of civilizations just keeps climbing.
Yeah.
More planets mean more civilizations.
Makes sense.
But the Solitude Zone, because it's focused on exactly one, forces the probability distribution into a bell curve.
A bell curve. Why is that shape so important for defining this zone of uniqueness?
because being unique is inherently fragile, statistically speaking. For px1 to be the peak probability, it has to be squeezed between two ways it could fail.
Failure modes. Okay, explain that.
Think about the rate at which complex life emerges. Let's call it the emergence probability. If that rate is too high, if life pops up easily all over the place.
Then you get lots of civilizations.
Exactly. Across the vastness of the universe, even a moderately high emergence rate would mean the probability of finding multiple civilizations, px1, becomes overwhelmingly large. The chance of finding only one drops to basically zero.
So the possibility of being unique collapses if life is too common. That defines one side of the bell curve, the upper limit.
Correct. Now let's flip the script. What if the emergence probability is extremely low, like astronomically low? Life is an almost impossible fluke.
Okay, well, intuitively, wouldn't that make the chance of finding only one instance higher if it's super rare?
This is the really critical insight that Veres emphasizes and maybe the most interesting part of the framework. When the probability of emergence becomes vanishingly small, something else happens mathematically.
What's that?
The expected number of civilizations across the entire universe actually drops below 1. Think about it. If the chance is 1 in 10 to the 100 per planet, even with 10 to the 24 planets, the expected number is incredibly tiny.
Okay.
At that point, the probability of finding exactly 0 civilizations, px0, becomes statistically much, much higher than finding exactly 1, px1.
I see. So if life is too rare, the most likely outcome isn't finding just one miracle. It's finding absolutely nothing at all. The universe finds it easier statistically to produce 0 than to produce precisely one ultra-rare event.
Precisely. That forms the other side of the bell curve, the lower limit. In a universe that's incredibly hostile to life, statistical silence is favored over statistical singularity.
Wow. Okay, so the Solitude Zone is that peak, that sweet spot on the bell curve where the probability px1 is higher than both px0 and px1.
That's the definition. It forces the conditions for life's emergence into this very narrow, specific window. Not too easy, not too hard.
This is brilliant because it immediately gives us a way to test different theories about the Fermi paradox. If your pet theory about great filters leads mathematically to either a universe teeming with life or a universe that's almost certainly barren, then that theory cannot place us in the Solitude Zone.
Exactly. The framework demands an answer to Fermi that walks a very fine line. Life has to be rare enough that we don't see crowds of aliens, but common enough that our own existence isn't a near statistical impossibility.
Let's really nail down those two defining conditions then. They seem central to understanding the results later.
Okay. Condition 1, the upper limit constraint. The probability that only one civilization exists at our K0.7 level must be greater than the probability that multiple civilizations exist at that level. So px1.
If life is easy, you fail this one. The universe gets crowded.
Correct. Condition 2. The lower limit constraint. The probability that at least one civilization exists, which is px1 plus px1, must be greater than the probability that none exists. So px1, px0.
And if life is incredibly, incredibly hard, if the great filter is almost insurmountable, you fail this one. Silence becomes more likely than even a single instance.
And that second condition is really powerful. It directly challenges those very pessimistic Fermi solutions that rely on something like abiogenesis being a 1 in a gazillion event. If it were that rare, the Solitude Zone model suggests the universe should statistically favor 0 life over just us.
So the model isn't just describing a zone, it's setting strict rules for entry. It's a high bar.
A very high bar.
Okay, we understand the structure now, this bell curve defined by 2 critical constraints. How did Dr. Veres actually plug numbers into this? What are the specific inputs he used? Let's talk about the 4 key principles of his model.
Right. These are the factors he uses, kind of replacing the vaguer terms in the Drake equation to specifically test for singularity.
Principle number 1 is complexity.
Yes. This is essentially a numerical scale to rank life forms. Veres defines it from 0, representing maybe the simplest single-celled organisms, potentially up to infinity for some hypothetical post-biological intelligence.
And crucially, this ties directly back to the Kardashev scale we talked about.
Exactly. By setting the target complexity level for his main analysis at K0.7, Veres anchors the entire calculation. He's not asking about bacteria, which might be common. He's asking about us, or beings like us, capable of harnessing planetary energy at our current specific level.
That makes it immediately relevant. The question becomes, is there another civilization out there right now doing roughly what we're doing?
Precisely. Now, the second and third principles are probabilities. and they sound similar, so we need to be careful to distinguish them.
Okay. Principle 2 is existence likelihood.
This is the broader probability. It's the chance that at least one civilization of a certain complexity level or higher exists somewhere in the entire universe. It reflects your general optimism or pessimism about life evolving complex forms anywhere.
So a high existence likelihood means you think complex life probably happens somewhere, somehow. A low one means you think it's generally very unlikely.
Right. Now, compare that to Principle 3, emergence probability. This one is much more specific and much more critical for the Solitude Zone math.
Okay, what's the difference?
Emergence probability is the chance that a life form of at least the target complexity level will arise in any single given potential system, like on one specific habitable planet.
Ah, so existence likelihood is about the universe as a whole, asking, is there at least one out there? Emergence probability is about a single location, asking, what's the chance life like this starts here?
You've got it.
Huh?
And it's this emergence probability, this per-system chance that Veres is really tweaking in his different scenarios. It's the main lever he pulls to see if the overall result across all potential systems satisfies the two conditions for the Solitude Zone.
That's the number that determines if we land on the peak of that bell curve or fall off onto the slopes where we're either crowded or statistically shouldn't exist.
Exactly. It dictates the shape and position of the bell curve.
And that per-system probability needs to be considered against the sheer number of possible systems. Which brings us to the fourth principle, the total number of potential systems.
Right. As we said, Veres expands the scope beyond our galaxy. He considers the entire observable universe.
And he uses a specific colossal number for the total number of potential places life like ours could emerge.
Yes, he locks this value in at 10 sub 24 sub. That's 1 followed by 24 zeros. It's the current rough estimate for the number of terrestrial or Earth-like rocky planets within the observable universe.
1 trillion planets. That number is just staggering.
It really is. And it sets up the core tension of the model to get exactly one success across 10 sub 24 sub trials.
The probability of success in any single trial, the emergence probability, has to be incredibly mind-bogglingly small. Roughly the inverse, right? Around 10 sub 24 sub.
That's the sweet spot the model is looking for. If the emergence probability is just slightly higher than that, say 10 sub 23 sub, you'd expect 10 civilizations. If it's slightly lower, say 10 sub 25 sub, you'd expect only be 0.1 civilizations, meaning 0 is the most likely outcome.
It really highlights the fragility you mentioned. The window for singularity, given the size of the universe, is vanishingly narrow. It's like trying to hit a specific atom with a single dart thrown from across the cosmos.
That's a great analogy. The Solitude Zone is mathematically trying to balance on that incredibly fine point.
Okay, so we have the framework. A bell curve definition of singularity based on complexity, existence likelihood, emergence probability, and that huge number of potential systems. Now for the exciting part, section 4. How did Dr. Veres actually run the numbers? What happens when you plug in different assumptions?
Right. He ran 4 main scenarios. Each one represents a different hypothesis about the nature and placement of the great filter, which essentially means inputting different values for that crucial emergence probability.
Let's start with the cheerful one, scenario 1, astrobiological optimism.
This assumes life, even complex life, is relatively easy. The great filters either don't really exist or they were trivial hurdles far in our past. Evolution just marches reliably forward on any suitable planet.
So, a high emergence probability.
Exactly. And the result is pretty immediate and predictable. The probability of humanity at K0.7 being in the Solitude Zone under this scenario is basically 0.
Why 0?
Because if the per-system chance, emergence probability, is high, then across 10 sub 24 subplanets, the outcome is overwhelmingly dominated by px1. Multiplicity wins. You fail the upper limit condition for the Solitude Zone.
Makes sense. If life's easy, we're definitely not alone. The universe would be teeming with civilizations at or beyond our level.
So optimistic scenarios rule out solitude. Now, let's flip completely to the other side. Scenario 2, the evolutionary hard step.
This is the highly pessimistic view, right? Placing a massive great filter extremely early in life's history.
Yes. For example, assuming abiogenesis, the initial spark of life itself, is incredibly rare, an almost miraculous event. This means the emergence probability is set to be extremely, extremely low.
Okay, so what does that do to the Solitude Zone probability?
It also crashes to near 0.
Wait, also 0? But for the opposite reason.
Exactly the opposite reason. If the emergence probability is pushed too low, the math favors px0. The most likely outcome becomes no advanced life existing anywhere, at all.
We fail the lower limit condition this time. Px01 is no longer greater than Px0. Even if we somehow beat the odds and exist, the model says statistically it's more plausible that nothing should exist.
Right. It highlights that critical insight again. Extreme rarity doesn't automatically lead to singularity. It leads to probable non-existence. So both the hyper-optimistic and hyper-pessimistic views fail to land us in that delicate solitude zone.
Fascinating. So to find a scenario where singularity is plausible, we need a great filter theory that makes complex life rare, but not impossibly rare, something in between. Yeah.
Precisely. Which brings us to scenario 3, the rare Earth hypothesis.
This is a well-known idea. The argument that while simple microbial life might be common, the specific conditions needed for complex animal-like life, let alone intelligence, are incredibly rare.
Yes, it posits a whole checklist of things Earth has that might be unusual. A large moon stabilizing our axis, plate tectonics recycling the crust, being in the right part of the galaxy, the galactic habitable zone, having a Jupiter-like planet protecting us from impacts, the right atmospheric composition, liquid water.
The idea is that getting all these factors right on one planet is extremely unlikely, even across billions of worlds. This acts as a significant filter, but one we've already passed.
Exactly. It makes complex life rare, setting the emergence probability low enough to likely avoid the PX1 crowding problem. But crucially, perhaps not so low that it triggers the PF0 non-existence problem across 10 sub-24 subplanets.
So does this rare Earth scenario fit the Solitude Zone criteria?
It fits remarkably well, according to Veres' analysis. It seems to strike that difficult balance.
And the resulting probability. What's the chance we are alone at KLI 0.7 if the rare Earth hypothesis is correct?
Under this scenario, Veres calculated the probability of humanity being in the Solitude Zone at 29.1%.
Almost 30%. Okay, that's a really significant number. It's not guaranteed, not even likely, but it's a very real possibility.
It suggests that if our existence truly is down to a series of planetary flukes, then cosmic solitude is a plausible outcome.
But Veres didn't stop there. He wanted to find the absolute maximum possible probability of being alone within his framework.
Right. That led him to create scenario 4, the critical Earth hypothesis. Now, this isn't a pre-existing astronomical theory like rare Earth.
What is it, then?
It's basically a theoretical scenario where Veres mathematically tuned the input parameters, especially the emergence probability, to the exact value that would maximize Px1, the peak of that bell curve, while still satisfying both the upper and lower constraints of the Solitude Zone.
So he reverse engineered the perfect conditions for solitude within his own model.
Essentially, yes, he asked. What emergence probability perfectly counterbalances the 10 sub-24 subsystems to make Px1 as high as it can possibly be according to this statistical structure?
And what probability did this perfectly tuned maximum solitude scenario yield?
It yielded the highest probability found, 30.3%.
30.3%. That's barely higher than the rare Earth scenario's 29.1%.
And that tiny difference is incredibly revealing. It shows just how narrow and sensitive that peak of the bell curve really is. Even when you deliberately try to maximize the chance of being alone, you only nudge it up by about 1% compared to a plausible existing hypothesis like rare Earth.
The statistical window for singularity is razor thin. The difference in the underlying emergence probability required to shift from a rare Earth outcome, 29.1% alone, to a slightly more crowded or slightly more empty universe must be minuscule.
Absolutely tiny. It really underscores the precariousness of the whole idea.
So let's go back and look at the big picture from these scenarios. Section 5. Key takeaways and implications. What's the headline finding?
The absolute headline, the most critical result from Veres' analysis, revolves around the 50% threshold.
Okay, what about it?
In none of the scenarios tested, not the optimistic, not the pessimistic, not rare Earth, not even the specially tuned critical Earth scenario designed to maximize solitude, does the probability of a K0.7 civilization like ours being in the Solitude Zone ever rise above 50%.
Never gets higher than 30.3%, in fact.
Correct. Which means, based on this statistical framework, it is always more likely that we are not alone in the specific sense of being the single unique instance.
So the math suggests it's more probable that either there are multiple other K0.7 civilizations out there,
or that the conditions are such that there should actually be none, and our existence is an anomaly the model struggles with statistically. But the scenario where we are exactly one is never the most probable outcome.
That's a really profound takeaway. Despite the silence, the statistics, when framed this way, lean against unique existence at our current level. We're likely either one node in a network, however sparse, or a strange outlier in a void. Singularity is the underdog scenario.
It suggests K.7 might be a relatively common stepping stone. Or, alternatively, that the jump to K.7 is already past a filter so severe that 0 instances is statistically more expected than 1. But exactly 1 doesn't seem to be the favored outcome.
Okay, but the model offered another major implication, didn't it? One that connects solitude to how advanced a civilization becomes.
Yes, and this is perhaps the most thought-provoking part philosophically. Veres found a distinct trend when looking at different points on the Kardashev scale.
What was the trend?
As a civilization's estimated Kardashev rating increases as it becomes more technologically advanced and harnesses more energy, the probability of that civilization finding itself in the Solitude Zone actually increases.
Wait, really? Becoming more advanced makes you more likely to be alone. That seems counterintuitive again. Why would that happen?
Think about the great filters again. If there are hurdles to becoming a Type I civilization, then surely the hurdles to becoming Type 2, mastering a star, or Type 3, mastering a galaxy, must be exponentially harder.
Right. Building a Dyson sphere seems orders of magnitude more difficult than just getting better solar panels on Earth.
Exactly. So each major step up the Kardashev scale likely represents passing another, even more improbable great filter. This means the emergence probability for reaching, say, Type 2 status is vastly lower than the emergence probability for reaching our current K0.7.
Okay, so the per-system chance drops dramatically for higher types. But the number of systems 10 sub 24 sub stays the same.
Correct. And what does that do to the probabilities? A much lower emergence probability drastically reduces the chance of PX1, the multiplicity outcome. It becomes incredibly unlikely that multiple Type 2 civilizations would exist simultaneously.
So as the chance of multiples collapses due to the extreme difficulty, the probability shifts towards PX1, singularity becoming the dominant term, assuming PX0 doesn't take over first.
Precisely. The model shows that for really advanced civilizations, think Type 2, or beyond, the probability of being the only one of its kind in the observable universe at any given moment actually climbs above 50%.
Wow. So the path to immense cosmic power is also, statistically, a path towards profound cosmic isolation. The more capable a civilization becomes, the lonelier it's likely to be.
It flips the script on the Fermi paradox for hyper-advanced civilizations. For them, the silence might not be a paradox at all. It might be the statistically expected state. They are the great filter, in a sense. Their own advancement is the rare event.
That suggests the ultimate great filter might not be a single cataclysm, but rather the sheer cumulative improbability of navigating the technological, sociological, and perhaps biological challenges required for continuous advancement on stellar and galactic scales.
It's a compelling interpretation offered by this framework. The filter is the climb itself.
So wrapping this up, what's the main value of this Solitude Zone model? It doesn't give us the answer, obviously.
No, it's built on estimates and assumptions, like any model in this field. Its real utility, I think, is analytical. It provides a rigorous mathematical structure for framing the debate.
It takes the very philosophical, "are we alone?" and turns it into a concrete statistical question. Under what conditions is PX1 maximized, and are those conditions plausible?
And by doing so, it acts as a filter itself. A filter for assessing different great filter theories. Does your theory predict an emergence probability that could realistically land us in that narrow Solitude Zone sweet spot? Or does it push us into the statistically more likely realms of multiplicity or non-existence?
It forces a level of quantitative discipline onto the discussion, which is valuable.
Incredibly valuable. Because until we get that unambiguous signal, or confirm the silence is absolute, models like this are our best tools for exploring the possibilities and guiding our search.
So to bring it back to the start, the question, are we alone? At our current K0.7 level, the Solitude Zone framework suggests the answer is probably not yes. The probability remains below 50%, likely below 30%.
It's statistically more plausible that we are either one of many civilizations at roughly our stage, scattered across the universe, or that we are a profound fluke in a universe where 0 is the norm. But being the unique singleton looks like the least likely option right now.
But the model also paints a fascinating picture of the future. The more we advance, the higher our Kardashev rating climbs.
The greater the statistical likelihood that we will become unique, that the silence we perceive now will become our statistically expected reality.
Which leaves us with a really provocative final thought. If solitude increases with advancement, what does that truly imply about humanity's long-term journey? If we aspire to become a Type 2 civilization, capable of harnessing our star,
are we also aspiring to a state where the odds are better than 50-50? That we are utterly cosmically alone? Is the price of ultimate technological mastery an acceptance of ultimate uniqueness and perhaps isolation?
It certainly frames our drive to explore and expand in a potentially more lonely light. Are we reaching for the stars only to find ourselves the sole occupant of the stage?
A profound question to ponder. Thank you for exploring the intricate probabilities and challenging ideas of the Solitude Zone with us today.
And thank you, our listeners, for joining this deep dive into the statistics of cosmic existence.